Okay guys, in this video we're going to be solving problem 6.21, and it says an experiment was run in a semiconductor fabrication plant in an effort to increase yield. 5 factors each at 2 levels were studied. The factors and levels were A. Aperture setting, small and large. B. Exposure time, 20% below and 20% above. C. Development time, 30 seconds and 45 seconds. D. Mask dimension is small and large. E. Etch time 14.5 minutes and 15.5 minutes. The unreplicated 25 design shown below was run as follows. Okay, so as you can see, I'm starting doing the Daniels test, and what I'm doing is just adding numbers from the top to the bottom in pairs. So I'm gonna complete this until I'm done here. Alright, now I'm gonna start subtracting from the top to the bottom the previous number, as well as we're doing it in pairs. Right after, since we have 5 factors, I'm gonna replicate the same with the last column. Okay, so once we get all the runs, all the 5 runs, we're gonna start getting the effects. And the formula is we get the 5th run divided by 1, which is the number of replicates, times 0.5 times 32, which is the number of data, and the coefficients is just the effects divided by 2. After getting the effects in point A, is asking us to get a normal probability plot of the effects to see which appears to be large. So we take the effects and sort it from smallest to largest, and get the probability, which will basically be the place minus 0.5 divided by 31, which is the number of data. We get all the probability, and we take those 2 columns to get a scatter diagram. And as we can see, A, V, C, and AV appear to be the largest, so those are going to be considered our significant values, and we're going to see that in the diagram. Okay, so to demonstrate what we just got in the point A, we're asked to conduct an analysis of variance to confirm, and we start by getting the sum of the squares of the main effects A, B, C, D, and E, and the 2 interaction sum of the squares. We get all the 2 interactions in the model, and the process is going to continue with 3 interactions, 4 interactions, and 5 interactions. All this is the sum of the square of those values divided by 1 times 32. The 1 means that it's just 1 run. Our problem didn't have but 1 run, and we continue with the process now with the 4 interactions. The total see the total we're gonna see that it's calculated differently, and we're gonna end up with the 5 interactions here with the A, B, C, D, E. The total is just the sum of the squares of the original data minus the effect, which is in the 5th run, square divided by 32. Now we're calculating the error, and since we're having no degrees of freedom in the error, everything including the f-test is going to be 0. We calculate the ms, which is basically the sum of the squares divided by the degrees of freedom, and then we're not prepared yet to run the f-test, but we're then asked to run the ANOVA test, and we start getting the sum of the squares. We get basically A, B, C, D, E, and all the factors squared divided by 32, and the total is going to be the same as in the analysis of variance. So as you can see, this is the same procedure to get the total. We get the error by subtracting all the factors, sum of the squares, by the total, and the degrees of freedom is 1 for each of the factors and 31 for the total. And yeah, we get 24 as the error. Degrees of freedom, we get the ms just dividing as well, degrees of freedom, sum of squares divided by degrees of freedom, and we get the F divided ms of each individual factor divided by the error. And there we had previously gotten the F, the calculated one, and we're running an if test just to see which ones are rejected or not, and the ones that are rejected are going to indicate the main factors that we're going to be studying. So we get that the first four are rejected, so there we have a confirmation for what we had previously got. Well, knowing that, we go down to write the model, the regression model, and we take A, B, C, and AV as the factors of our regression model. We copy the coefficients for first the main one, then for A, as we can see there. We go and do the same for B. It's we get the coefficient, and the same we do for C and for AV. What we're gonna do is just copy those for all the 32 lines that we're gonna do. We're looking to get the signs of A for the to be able to multiply that, the signs of V for the factor V. We do the same for with the signs of C, as they are already pre-established, and the same well, A and B is product of the signs of factor A and factor B. Right, getting that, we go and copy the values for all the column. We just copy it as values. And with this, what we're looking to get is pretty much the residuals, where we are gonna compare to the expected and what we observed during the model. So we're getting there the expected, and we simply follow the formula, which is the model multiplying the coefficient times the sign of the factor. We compare then to get the residuals, and there we have the residuals. We go ahead and go to point D, which asks us to plot the residuals to see if it's satisfactory. So we sort it from the smallest to largest. We get the probability in the same way that we had done before, and we go ahead and select the residuals and probability and get a scatter diagram. And from that we can conclude that yes, it is satisfactory. And now we're going to point E, which we're comparing the residuals against the yield, and now we're doing it to A, and we're comparing
and
the
from
residuals
here we can see
against
already
the signs of
factor
B.
A and B, which are the significant factors, and when they are in high or in low are the ones who affect the results of our experiment. We still need to plot D and E, but we already know A and B are the ones that we need to look at to be able to have our experiment under control. After concluding that, we get to the final of our model, and it's asking us to give our recommendations, and we start studying each factor at a high and low level. So we get the averages, just studying everyone with respect to the sign. When A is in the low or A is in the high, we get the average of that, and we get the same for A
low, A high, B low, B high, and we continue moving forward like you can see on the factor B. It's minus minus plus plus, and that's how we select the factors of the yield. Continue getting the results. And we start seeing from here we're gonna do the graphs here in the same point E, but we start seeing that in A, B, and C, the low and high have a lot of difference between those two. So we're gonna see that in order to increase the yield, we're gonna have to look at those factors. Now we start getting the graphs. We select the -1, +1, and the averages of when they're low and high. And we get first A. We continue with B. Well, we see that there are two main differences, and they're marked. There are big difference between when it's high and when it's in low. Then we're gonna compare the factor C, and we also see that we need to be taking care of C if we are to increase the yield. What we want to do is to keep A in high, B in high, C in high, and D might appear in the graph as it's significant, but it's really not if we look at the scale that it gives us. It is not a big difference. There are decimals, the difference between those two. So from here we can conclude that A, B, and C are the factors that are, in order to keep the yield high, we need to maintain high. D and E doesn't really matter.